Hello everyone. Today my topic is lanthanide contraction. We know that as we move down a group, atomic size covalent to ionic radii normally increase. This is mainly due to the additional shells or electrons between the successive periods. However, as we move across a period from left to right, atomic size decrease. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell or electrons attracted more and more. Consequently, the size decrease. For example, the covalent radii of alkali metals increase from lithium to cesium, and for halogens from fluorine to indium. If we consider the ionic radii of lanthanides, we get very interesting observation. For comparison sake, we can take the ionic radii of trivalent ions M3 positive, which are most stable. These are shown in figure 2. You can see the figure. These are shown in figure 2. It is clear that ionic radii decrease from one element to another in the lanthanide series. Decrease is very small. It has been observed that from cesium cerium 3 positive to lutetium 3 positive, the ionic radii decrease from 1.03 angstrom to 0.86 angstrom. Table 7. You can see table 7. Now again, obviously for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to elements of other groups and periods. Similarly, on moving from cerium to lutetium, the atomic radii also decreased from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic or atomic size of the lanthanide elements with increase in atomic number is called lanthanide contraction. Now, causes of lanthanide contraction. In lanthanide series, the 4f electrons are being added one at each step as move from one element to another. The shielding of one f electron by another from the nuclear attraction is quite weak due to the shape of f orbitals. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increase. Hence, the inward pull experienced by the 4f electrons increases, and this causes a reduction in the size of atom or ion. The sum of successive reduction gives the total lanthanide contraction. Consequences of lanthanide contraction. Lanthanide contraction has very significant effect on the relative properties of the elements which precede and which follow the lanthanoids in the periodic table. Some important consequences of lanthanide contractions are given below. First, a steady decrease in size. There is a regular decrease in the ionic radii of lanthanides. Second, electronegativity. This is slightly regular increase in the electronegativity of the trivalent ions. Third, electrode potential values. There is small but smooth increase in standard electrode potential values for this process. M3 positive plus 3 electron gain aggregate results to metal. For lanthanum, 2.5 to V2 minus 2.25 V for lutetium. Resemblance of second and third transition series. The lanthanide contraction affects the chemistry of second and third transition series, as we can see from table 8. You can see the table 8. Now, there is a regular increase in size from scandium to uranium to lanthanum. Similarly, we expect normal increase in size in other groups. However, after lanthanides, the increase in radii from second to third transition series almost vanish. The pair of elements this etc. possess almost the same size. The properties of these elements are also very similar. As a result of lanthanide contracts, the elements of second and third transition series resemble each other much more than the elements of first and second transition series. Similarity among lanthanides. Because of the very small change in the size of the lanthanoid ions in lanthanides, their chemical properties are similar, therefore their separation becomes very difficult. Recently, methods based on repeated fractional crystallization or ion exchange techniques, which take the advantage of slight difference in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size difference in their trivalent ions have been used. Now, sixth point, a basicity difference. Due to lanthanide contraction, the size of lanthanide ions decrease regularly with increase in atomic number. As a result of decrease in size, their covalent character between Ln3 positive ions and OH negative ions increases, and therefore the basic strength of hydroxides decrease with increase in atomic number. Thus, LaOH ki thrice is most basic, then LuOH ki thrice is the least basic. The basicity difference in lanthanides are reflected in increasing tendency to get hydrolyzed due to decrease in basic character. There is slight increase in degree of hydrolysis in solution from La3 positive to Lu3 positive. Example, La3 positive ions are less readily hydrolyzed than Lu3 positive ions. Thermal decomposition of oxysalts. More basic oxysalts decompose less readily. Example, LaNO3 ki thrice decompose with difficulty and it is stable, whereas LuNO3 ki thrice is unstable and decompose readily. Solubility of salts. Lanthanide hydroxides precipitate at regularly decreasing pH value from La3 positive to Lu3 positive. Seventh है size of some elements. Due to lanthanide contraction, the radii of Yb3 positive is comparable to heavier lanthanides Tb, Dy, Ho and Er, therefore they occur together in natural minerals. 8th, reactivity of lanthanoids. All the lanthanoids are highly electropositive metals and have almost similar chemical reactivity. This is due to the fact that the lanthanoid differs only in the number of 4f electrons. Since these electrons are very effectively shielded from interaction with other elements by overlapping 5s, 5p and 6s electrons, they show very little difference in their chemical reactivity. Because of their similar chemical reactivities, their separation from one another is very difficult. The lanthanoids are in general more reactive than d block elements. Some of the chemical characteristics are: first, they tarnish readily on exposure to air in finely divided state. All burn in air to form sesquioxide to the formula Ln2O3, where Ln stand for lanthanide, except cerium, which gives CEO2. Deuterium, however, resists the action of air even at 1000 degrees Celsius due to the formation of a protective coating of its oxide. Now, solubility of compounds. The fluorides, oxide, hydroxides, carbonates, phosphate, chromates and oxalates of lanthanoids are largely insoluble in water. On the other hand, the halides other than fluorides, nitrate, acetate, perchlorates and salt of oxoacids of lanthanides are soluble in water. The solubility behavior of salt of lanthanoids follow the pattern of solubility of salt of group second elements. However, lanthanide sulfate, unlike the sulfate of group second elements, are soluble in water. 10th है tendency to form complexes. Although the lanthanides ion have a high charge +3, yet they have large size of their ion compared to the transition metal. As a result, they have low charge density and therefore they have very less tendency to form complex. Their complex with unidental ligands are very few and form complex only with fluorine and oxygen donor ligands. However, they form complex with a few chelating ligands such as beta diketones, oxamines and ethylene diamine tetraacetic acid, alpha alpha dipyridyl and hydroxycarboxylic acid such as citric acid. These complexes usually have high and variable coordination number, and water or solvent molecules are often attached to the central metal atom. Beta diketone complex of EU3 positive and PR3 positive dissolved in organic solvents are used as lanthanoid shift reagents in NMR spectroscopy. In contrast to the transition elements, the coordinate number of 6 is not very common. Coordination number below 6 is also uncommon and occurs only with bulky ligands such as 2,6-dimethylphenyl and N-SIME thrice-twice ligands. However, coordination number 7, 8 and 9 are common and these give a variety of stereochemistries. For example, the coordination number for LNOH twice N3 positive charge in aqueous solution are thought to be 9 for early lanthanides and 8 for the later smaller member of the series. However, these ions are highly labile. The smaller ytterbium ion YB3 positive forms 7 coordinated complex like this, and their larger L3 positive is 8 coordinated in like this, where ACAC is acetyl acetonate. The structure of these complexes are a capped trigonal prism and a square antiprism as below in figure 3. Coordination number 10 and 12 occur with the larger, lighter lanthanoids and small chelating ligands such as NO3 negative and SO3 2 negative. You can see the figure. Now the last point है double salt formation. The lanthanide salt form double salt with corresponding salt of ammonia and alkali metals. Example NH4 twice SO4 into Ln2 SO4 thrice into 8H2O and many more examples etc. Double salts like alums with 24 water molecules are not formed. This is because the lanthanide ions are so large that these cannot coordinate to 24 water molecules octahedrally as in alums. Now our lanthanide contraction and its causes are complete. Thank you.